Is y'all doing okay so far with the material? Some of you might think it's a little easy. It'll get more difficult as we go along. And some of you might be a little bit behind. I expect some of you are. So if that's the case, like I said, please come see me. You need to be working on the homework, on the old exams. The exams are not that far away, so you should be prepared to go along. Let's continue on in chapter 2. We're defining things. You recall we defined the displacement last time. That's just the difference in the positions, the final minus the initial position. And then we also define sort of vector and scalar quantities. Remember, vector quantities have magnitude and what? Direction, right? And then scalar quantities just have magnitude. So things that are scalar include things like time, mass, charge, volume, area, length, stuff like that. And then vector quantities include a lot of what we'll do in kinematics: velocity, displacement, acceleration, also force, momentum, things that we'll deal with throughout the semester and into next semester, like magnetic fields and currents and such as that. Or not currents, but well, we'll deal with that next semester. Then we define average velocity. We won't use average velocity a whole lot, but average velocity will become very important when we define what we call instantaneous velocity. So it's just the displacement over the time, the change in the position over the time interval. And so, say for example, we have a plot of position versus time, and we'll make one of these in just a little bit. And in the lab, you'll deal with these kind of plots quite a bit. So this is just a plot of position. So at time 0, my object's at negative 20 meters. At time 10 seconds, it's 0 meters and on. So it's a position on the y-axis, time on the x-axis. So the slope of the line gives the average velocity. Over the interval from t equals 0 to 30 seconds, which is our full interval for the time. Because remember, average velocity is delta x over delta t, and slope is rise over run. And so on this plot, these are the same, because the rise is my change in x, and my run is my change in t. So the slope of our position versus time graph is the velocity. The slope of the position versus time graph is the velocity. So here, if I take that slope, my average velocity is delta x over delta t, which is my slope, rise over run. And going from 0 to 30 seconds, my final position is going to be 40 meters. My initial position is going to be negative 20 meters. So that gives me a displacement of what? What's my displacement? Going from negative 20 to 40 meters. This is going to be 60, right? So it's 40, which is my initial position, my final position, minus negative 20, which gives me a total of 60, as Courtney said. And then the time is going to be 30 minus 0. And then that gives us our slope, 60 over 30, which is 2 meters per second. Now, on this plot in particular, because the slope is unchanging, the slope is always constant, that is, it's a straight line, you can take intervals elsewhere and you'll get the same average velocity. But that's only because the slope isn't changing. So say, for example, I go from point A to B. I don't know my average velocity there. It's going to be delta x over delta t, which is 0 minus negative 20. Divided by my time, which is 10 minus 0. So this is in meters, this is in seconds. That's going to be 20 divided by 10, or 2 meters per second. All right, so I get the same slope there, too, that I did over the longer interval. But that should be obvious, too, because the slope is unchanging, so it doesn't matter what interval it takes, the slope will be the same. Is that obvious? Yeah? Okay, good. Now we will deal with graphs that are... Okay, so because the line is straight, and the velocity doesn't change, the average velocity from 0 to 10, which I just showed you, is the same, and that average velocity was 2 meters per second. All right. Now, often the case is that we'll deal with position versus time graphs that are not linear, something like this, and then our average velocity we'll calculate in much the same way. So say, for example, on this graph, I wanted to know the average velocity from certain time intervals, say from 0 to 10 seconds. I want to know the average velocity. So I want to know the average velocity over this time interval. I'll do it just the same, all right? I'll pick a point here, and I'll pick a point here, and I'll just calculate what is the slope. So it's as if I'm connecting these 2 points with a straight line, and I'm asking what is the slope of that line. All right, so I'll just pull my delta x and delta t off of that graph. So my average velocity is delta x over delta t. My x final is going to be what on this? For this graph? What is it? It's 30, right? So my x final is the position at this time, which is 30, and my x initial is 20. So it's 30 minus 20. And my time interval, of course, is 10 seconds. So 10 minus 0 seconds. So that's 10 over 10, which is 1 meter per second. All right, so that's my average velocity over that time interval. But if I change the time interval, say instead I go from 10 to 30 seconds, so that's going from this point to this point, you have a lot of variation in the velocity as I go throughout because the slope of that graph is changing. But when I find the average velocity, I just want to know the slope of that line. Right, so I disregard anything that happens in between the 2 points. So I have it slowing down and then speeding up again and slowing down. I take the slope instead of this line. The average velocity is not dependent upon what happens between the initial and final points. It's only dependent upon the initial and final points. All right, so I can find that average velocity from 10 to 30 seconds. Just like my final position is minus 20, my initial position is 30. So minus 20 minus 30 meters divided by my time interval, which is 30 minus 10 seconds. And then that's equal to negative 5 meters per second. You'll definitely have some graphing problems on the test, and we'll work through some a little bit later. And you'll probably have a very simple question, just like this: what is the average velocity over a time interval? But then we'll continue on with some other questions regarding that, okay? But you'll need to be able to just pull what is the average velocity off of a graph like that, be able to interpret the graph in that way. Yeah?
What is it, 5 over 2?
Is it point? Let's see. Yeah, you're right. So negative 50 over 20. Sorry about that. I had it incorrect in my notes. So that's negative 50 over 20, which is negative 5 halves, negative 2.5. Thank you both. All right. Y'all can do this. It's pretty straightforward, right? You're just pulling numbers off a graph, really. But you need to know what that definition of average velocity is. Average velocity is really important when we're defining what is instantaneous velocity, because our definition of instantaneous velocity is dependent upon our definition of average velocity. So we're going to label instantaneous velocity with V with a little arrow over it. In fact, most of the time when we're talking about velocity, like if I just say velocity, I'm implying the instantaneous velocity. And it's just the velocity at a particular time or a particular instant. Whenever we talk about instantaneous velocity, it's just the velocity at a particular time or an instant. That's why we call it instantaneous. And usually when we measure velocity, we're measuring the instantaneous velocity, not the average velocity. So, for example, a speedometer in a car gives the magnitude of the instantaneous velocity. What it does actually is it calculates actually an average velocity, but over a very, very small time interval. And so we call that the instantaneous velocity. Right? So as your car is traveling along, it'll calculate the distance that you travel divided by the time, And that's an average velocity, but for a very small time interval, which is the same as the instantaneous velocity. All right, we're going to define it in this way. It's the limit of the average velocity as my time interval gets very, very small. Right, so my instantaneous velocity, this is my average velocity, but I'm going to let the time interval get really, really small. Just like your car, when it measures your speed for your speedometer, it's really measuring the average velocity, but for a very small time interval. Right? And then that is the instantaneous velocity. What is this the definition of? What does this look like to you? This limit as the denominator goes to 0 of this quotient. What is that the definition of? Like in mathematics, what is it the definition of? Or in calculus? It's the what? No. No. Does this look like anything to you? That's where they got away here. But what is this? In calculus, what do we call this? The what? It's the derivative, right. So this is just the derivative of x with respect to t. So we define the average velocity, or the instantaneous velocity, as just the derivative of the position with respect to time. All right, so the instantaneous velocity is just the first derivative of the position with time. So in a nonlinear graph, I have it on the next page, the slope of the tangent line is equal to the instantaneous velocity. I'll draw a picture about that, show you what I mean. So the derivative is really just a fancy way of finding the slope of a line, or the slope of a function at a particular point. And since the slope of our position versus time graph is the velocity, then we can use the derivative to find the instantaneous velocity at a particular point. Right? So Newton actually developed calculus to deal with describing motion of objects. And so we'll use a lot of what he developed, the derivative and the interval, in order to analyze functions that describe the motion of particles. Okay? Have y'all gotten to this in calculus yet? Derivatives? Are you still doing limits? Limits, okay. We all get to this, so this is sort of, this is a useful part of calculus. So if you have a nonlinear graph and you want to know the instantaneous velocity at a particular time, say I want to know the instantaneous velocity here, I draw a tangent line like that, and the slope of that tangent line gives the instantaneous velocity at that point. Right, so the slope of the tangent line, that equals the instantaneous velocity. The tangent line has a mathematical definition. It's something about, I forget exactly, but these 2 points are equidistant from this point. But I always just like to think of it as a seesaw, that when you draw a tangent line, which you'll be estimating some tangent lines in the class, is that you just have this line so that it's like it balances on this function. All right? Whereas, so that's a tangent line, but for example, at this point, this is not a tangent line. Right? So that's not a tangent line, that's just sort of a line drawn off. But you want it so that it's like it balances on that function. You understand what I mean by that? It's tangent to the function. If not, we're going to do a few practice problems, and you'll see some in the homework as well in the old test. It'll give you some practice. Let's see, let's try this. This is a quick test question. I just want to know, what is the instantaneous velocity at t equal 4 seconds? So what you'll need to do there is to draw a tangent line at the function at t equal 4 seconds. It should be fairly easy because at 4 seconds the function is fairly straight, and you can draw a line that is tangent to that function, and then determine the slope of that line. Wait a minute. That's good. And then if you finish that question, you can go and answer the next question, which is, what's the average velocity between t equals 0 and 2 seconds? I'll show that question in just a second. What's the average velocity between t equals 0 and 2 seconds, between this point and this point? But right now you're answering this question. The instantaneous velocity at t equals 4 seconds. Okay, just take a minute to turn to your neighbor and tell them what you got. Compare your answers. Is your answer going to be positive or negative? Is the slope of that tangent line positive or negative?
Positive.
Right, it's positive, so D is not a possible answer, though I see that at least a couple of you have put D. The slope of this line is definitely positive, all right? Whatever this tangent line is. If it's not negative, it has a positive slope. So the answer is definitely not D. All right, I'm going to stop here in just a second. I'll stop at 2:30. Just guess if you don't know. All right, we're sort of split between A and B. A is the right answer. Let me show you. You can draw your tangent line. Look, something like this. This takes practice. You'll get the hang of it. Something like that. And then you just want to find the rise over the run. Oh, wait, no, actually. Did I put A or B as the answer? Yeah, that's right. Okay. All right, so now I want to find my rise over my run. My delta x, that is my change in my position. It goes from 3 to -3. So that's 3 minus -3. So that's equal to 6. So my rise is 3. And then my run, which is delta t, it goes from 5 seconds to 3 seconds. That's 3 seconds. So I have 6 meters over 3 seconds. I'm sorry, not 3 seconds, 2 seconds here, because it goes from 3 seconds to 5 seconds, and so that is 3 meters per second. Those of you that put 1.5 meters per second, probably what you did is that you counted the squares here. That's a common mistake, and that's why I put 1.5. You see, if I count the squares, I get 1, 2, 3, 4, 5, 6, which is correct here because each square corresponds to 1 unit, or 1 meter. But over here, each square corresponds to a half a second. But if you count the squares, 1, 2, 3, 4, and then you do 6 divided by 4, you'll get 1.5. That's probably what you did. Is that what you did? Those of you that put 1.5? Not saying. Okay, that's probably what you did. And that's not the correct way to interpret a graph. Remember, graphs have scales, and you have to interpret the scales properly. It's not possible really to fit an actual line with a slope that's half this. That would be in any way conceivably the tangent line. So it would look, well, a slope of 1.5 would look like something like this. It would be a lot shallower than the actual function. Right, so the answer has to be positive because it has a positive slope. And really the only conceivable answer here is 3. There might be some judgment call as to where you draw your tangent line, but you can't really get any of those other answers. All right? You'll do this in lab if you haven't yet. We do a lab, the second lab, with a lot of interpretation of graphs, and we'll do some more as well. All right, let's do the second problem. Let me erase all this. Can all this go? We need to find the average velocity. If you have your book, this question's on the just below here, but I'm going to write the options here. I want to know the average velocity from t equals 0 to 2 seconds. And the options are this: A, -2, B, -1.5, C, -1, and D negative 2.5. These are meters per second, all of them. So what is the average velocity from t equals 0 to 2 seconds? Negative 2, negative 1.5, negative 1, or negative 2.5? All right, I'm going to stop at 115, which looks like everybody's in. 115. Okay, that must be right. Let's go ahead and count it. All right, so what was that, B that I marked? That was B, right? Right here. Negative 1.5. To do that, we just pull the numbers off. We have delta x over delta t. We're not drawing a tangent line here, though. We're just pulling the numbers off, so that x from 0 to 2, x final is negative 4, x initial is negative 1. So negative 4 minus negative 1, 2 minus 0. This is in meters, seconds. That's negative 3 over 2, which is negative 1.5, which is right, B. All right. Let's do a quick little for this. Yeah, before we move into acceleration, let's do a quick little graphing exercise. I'm going to need a few people. Do you have cellular phones with timers on them, a smartphone? I need a few people. We're going to do a little exercise where we take a car. I'll follow along here for a second. Where you take a car. This car travels along at constant velocity. And we're going to take some quick data just as it moves along the track. We'll use these tiles here. We'll say that these tiles are a meter. They're not quite a meter, but we'll say that they are. And we'll have several of you that will be taking time, and you're going to measure the time as the car travels from 0 meters right here. We'll have somebody here to measure the time it takes to travel 2 meters, somebody that takes the time it travels 4 meters, somebody takes the time to travel 6 meters, and then maybe up here, and we'll try to do 8 meters as well. All right, so we'll the car travel along, and then you timekeepers will be taking time, measuring the time that it takes to travel on those different distances. And what we're going to do is we're going to create a position versus time graph. I've done this in Excel. I've just sort of set it up where we'll plot out the positions, 0, 2, 4, 6, 8 meters, and then we'll record the time elapsed. And then I'll show you how we can find the slope of that line in Excel, and that'll give us the velocity. And then we'll also look at the velocity versus time graph, which we haven't gotten to yet, but it also contains a lot of information about the motion. All right, so I need a shepherd who can do that for me. This is going to be the person that will just take the car and sort of keep it going in a straight line. Who would like to do that? All right, Michaela, can you do that for me, please? And then I'll need some timers. So Michaela, what you're going to do is you're just going to start it. Don't go there. If you just want to keep it sort of make sure it goes on a straight line. You just do that. Can you hold that? All right. Let's see. Do you have a cell phone? Yeah. Okay. Why don't you do it here? So you can just stay in your seat actually. And when it crosses this line, I'll tell you when to start. When Michaela starts it, and when it crosses this line, I'll tell you when to stop. So you'll stop your cell phone. Let's see. Hunter, do you have a cell phone? All right. Can you come up here? So when it, let's see, I forget your name. Jan. All right, so Jan, you sit there. And Hunter, you'll be here. When it gets here, you'll stop it when it crosses this line. And then I need somebody else. Corey, right? Is it Corey, do you have a cell phone? With a timer on it? Okay. Why don't you come up here and you'll stop it when it gets here. Alright, so I'll give Michaela a little space, but you need to stop the timer, or you need to start the timer when I say go, and then you need to stop it when it reaches your line. Okay? Michaela, you ready? Start it back here, and then I'll tell them when to start. Okay, y'all start your timers until I say go. You want to keep it going in a straight line. We'll redo it. Okay, Michaela, bring it back. Redo it.
Yeah, I was using something else.
Okay. Are y'all ready then? So restart your timer.
Hold on.
Alright, Michaela, you ready? Start. Stop. You got him?
I think I'm gonna have to redo it.
Okay, one more time.
I'm using an app that I have. I can't even find mine on my phone.
Alright.
Alright, hold on.
Just a second, Michaela. Just a second. Got it, Corey?
Yeah.
You got it okay? Alright. Start. Alright. Y'all keep your times when I call on you, please give it to me. Y'all can have a seat. I'll take that with you. Thank you. Alright, so our distances here are 0, 2, 4, and 6 meters. And our time initially was 0. Who was our first timer? I forget. Oh, Young. Yeah, what's the time? 4.16. What's the next one? 8.18. So see, roughly twice. And what was that last one, Corey? 14.2. All right. So now we have our data. It's our data. You can tell it's pretty much a straight line. It looks like, Corey, it looks like you might have underestimated that timeline. It looks like it should be a little bit higher. And roughly it doubles every time, right? The time that it takes. It's moving at this constant velocity. Let's fit a line to it. Got to do linear regression in Excel? You should have in chemistry. And we'll do it in class as well in the lab. But you just click on the data points, you right click, add trend line, and then you can add a linear fit. You can do other fits as well. So if you know that you have a quadratic function, you can fit a polynomial, the second order, third order, whatever you want to do. You can fit a logarithm to it. Here I'm going to, and I'm not going to do that. I'm going to display the equation and see how good our fit is. And so it looks like our object, the slope of this line is 0.4 meters per second. And so that tells us that that this object is traveling at 0.4 meters per second. That's the slope of the line. And it's a pretty decent fit. All right? So if I were to plot the velocity versus time, what would it look like for this constant velocity car? Does the velocity increase or stay the same for this car? Stays the same. And what would it look like, a velocity versus time graph? Would it look like this, this, or this? It's just going to be a straight line. So if I plot that velocity versus time, see if I can draw it here. My velocity versus time, it's going to look like this. All right. This value of the velocity right here will be the slope of our graph, which is 0.42. I'll just call it 0.4 meters per second. And that means that this car travels along 0.4 meters every second. Something that we'll get into in just a little bit is that we can find what is the total distance that's traveled. by taking the area under this velocity versus time graph. We'll get into this in just a little while, but if I want to find the area under a graph, what is that called in calculus, to find the area under a graph? That's the interval. So we'll do that later, where we actually take the interval of a function over time, and that'll tell us the distance that's been traveled. So if we take the derivative of a velocity function as a function of time, that'll give us the distance that it's traveled. So I can do that. This is a pretty simple calculation. I can find the area under this graph at 0.4 meters per second. Our time went up to 14 seconds roughly, and so I can say 0.4, this is just a rectangle, right, times 14 seconds, this is meters per second. That gives me what, 440, 56, 5.6 meters. All right, 5.6 meters. We know it traveled how far, roughly? It traveled 6 meters, right? We had a person at 2, 4, and at 6 meters. So it traveled 6 meters, but because of this last data point, our velocity is actually a little lower than it actually is. So, Corey, no offense, but like I said, this time should have been a little higher, and so this slope should have been a little steeper, which would give you a slightly higher velocity for the car. We're going to do all of this as we go through the next week or so, interpreting these graphs, taking derivatives and intervals in order to find these particular values about an object moving. All right. Okay, so with that, let's go ahead and define what acceleration is. I'll take this away. Let's see. What's the looking like it's Monday out there. So what's the worst thing about living on O Street? Does anybody know? See, now, like when we tell jokes, this is what you do. I ask you a question, and you say, I don't know. What's the worst thing about living on O Street? Huh? I don't know. Right. I don't know. That's the appropriate response. The worst thing about living on O Street is that you got to walk a whole block to pee. You get it like O Street, P Street. Okay. Okay, so the acceleration, we've already talked about this a little bit. It describes how the velocity changes with time. Remember, the units of this were meters per second, or meters per second squared, as we usually write it. It says for every second, how much does the meters per second change? For every interval of time, how much does the velocity change? And just like we do with average velocity, we'll have an average acceleration. It's going to be delta V divided by delta T, VF minus V initial over the total time. Here, I'm not even going to bother giving the initial time because we'll assume that that initial time is 0. So for example, if I had an initial velocity of 10 meters per second and the final velocity was 20 meters per second, then I could calculate my average acceleration 20 meters per second minus 10 meters per second divided by 2 seconds minus 0 seconds. That's 20 minus 10 is 10 over 2, which is 5 meters per second squared. All right. Average acceleration is not terribly useful. Usually when we talk about acceleration, we'll talk about what type of acceleration. Like we did with velocity, like we don't usually talk about average velocity, we talk about what? Instantaneous, right. And the same will be true of average acceleration. Not going to use it a whole lot, but we'll use it to define what is instantaneous acceleration. Okay, I just want to give this little rule here. This will become important as we start to do free fall problems and dealing with different kinematics problems. If the velocity and acceleration are in the same direction, the speed increases. If the velocity and the acceleration are in opposite directions, the speed decreases. What that means is that a negative acceleration does not necessarily mean slowing down. Right? A negative acceleration can mean speeding up, if what is true. When can a negative acceleration mean speeding up? If what? Right, if the velocity is negative. So a good example is free fall. So if I drop this, it's going to accelerate in the negative direction, right? It's also traveling in the negative direction, so it speeds up as it falls. Now on the other hand, if I throw it up in the air, the acceleration is negative, but the velocity is what? It's positive. So if I throw it up, it's going to slow down. So as it goes up, it slows down, and then as it comes down, it speeds up. But in all cases, the acceleration is negative. Right? So negative acceleration does not mean deceleration. Negative acceleration just means accelerating in the negative direction. Sometimes negative acceleration means deceleration, like when it goes up in the air, right? That's decelerating, but only because the acceleration and velocity are in opposite directions. So the point is, negative acceleration does not mean deceleration. So acceleration can be negative, even when the object is speeding up. And it can be positive, even when the object is slowing down. All right. Also, negative acceleration does not mean deceleration. All right. Remember, our negative, when we're talking about vectors, our negative refers to direction, not the rate of change. And deceleration implies a rate of change. All right. My negative only gives the direction. I think I've already done it. Oh no. So here, if I have a car that has these initial and final velocities, I can find the average acceleration. Y'all go ahead and try it. I'll give you just a second to get a little head start. What is the average acceleration of this car? What is it? You might know? -5 is right. Right. So I say VF, which is -20, minus -10, divided by 2. And that gives me -10 over 2, which is -5 meters per second squared. So here I have a negative acceleration. All right, my acceleration is negative. But notice that here I have a magnitude or a speed of 10 meters per second, and here I have a speed of 20 meters per second. So this car is speeding up, but it has negative acceleration. So it's speeding up in the negative direction. The car has a negative acceleration, but it is actually speeding up. Okay, so if we were to sketch the velocity versus time graph for that scenario, it would look like this. See, what were my... I had an initial velocity of -10 meters per second. So right here, we'll call this -10. I'll call this -20. And so if I were to plot this, it would look like this. My velocity versus time graph would look like that. Now, the slope of a velocity versus time graph is what? It gives the acceleration. If you ever forget what the slope of a particular graph is, you can just look at the units. So here I have the units of velocity or meters per second, and the units of time or seconds. And slope, of course, is rise over run, so it's meters per second over seconds, and then that gives you meters per second squared. So you can always just look at the units to figure out what is the slope, or what does the slope represent. Likewise, if we were to find the area under this graph, we would find what? The distance traveled. And again, you can look at the units, meters per second, times seconds, gives us meters, and that gives us the distance traveled. All right, we're going to look at some various velocity and position versus time graphs and interpret them, and that'll be a pretty major portion of your exam. Okay, so instantaneous acceleration is defined in this way. It's the limit as delta t approaches 0 of the average acceleration, delta v over delta t. And of course, this is just the first derivative of the velocity with respect to time. Or if you want to write it again, since I know that v is equal to dx dt, how is the acceleration related to the position in derivative? It's the second derivative, right? So this would be the same as writing d dt dx dt, the derivative of dx dt, which is the second derivative of x with respect to time. All right? We'll show some examples where we take those derivatives. I'll give you a function for the position, and then you'll need to give the velocity and the acceleration functions for that particular object. But the acceleration is the first derivative of the velocity and the second derivative of the position function. There will be a question on your exam where I give you a function, probably it might even have a graph attached with it, and you have to take the derivatives of that function and report the velocity and or acceleration and give some other particulars about it. We'll work through some examples later. All right, so the acceleration is the slope for the tangent line. Since it's the derivative, it just gives a slope on a graph of velocity versus time. So just like we did before, if I want to know the acceleration at a particular time, say if I want to know it at this point, I find the tangent line at that point. Or if I want to know it at this point, I find the tangent line at that point, and that'll give me the acceleration. Is this a positive or a negative acceleration here? It's a negative. It has a negative slope, so it's a negative acceleration. How about here, positive or negative? Positive. Which has the greater magnitude? Which one is accelerating at a faster rate? The one on the left or the one on the right? The one on the right has a steeper slope, right? So it's a steeper line as opposed to that shallower line. Okay, so if acceleration is constant, as it is in this graph, just like we had before with that velocity, the position versus time graph, where we said it was a straight line, and in that case it didn't matter what interval you took, your average velocity was always the same. The same is true here. If acceleration is constant, the average acceleration is equal to the instantaneous. All right? It's not supposed to be a groundbreaking comment. It's just saying that the slope here doesn't change. So it doesn't matter if I take the slope over these intervals, or these intervals, or these intervals, or at a particular instant. The slope is always going to be the same. And so the average acceleration is equal to the instantaneous acceleration. That was just like we had with the average velocity equaling the instantaneous velocity. All right, let's try working with this function. Here's a position function. As we said, the velocity is the first derivative of position. The acceleration is the second derivative. I want to know, for this function, what is the velocity at t equal 3 seconds. So I want you to go ahead and try taking the derivative of this. If you recall, if I have a function x equal at to the n, then the derivative of x with respect to t is going to be a times n times t to the n minus 1. All right, so go ahead and try taking the derivative of that function and then evaluate it at 3 seconds. So go ahead and take the derivative and then just plug in t equal 3 seconds and tell me what is the velocity at that point. You don't have it yet? What is it called?
I'm not sure, it's been a while since I've done derivatives, but 15?
That's right, yeah. So the derivatives we do in this class, they won't be terribly difficult. Later, when we get into oscillations, we'll do some chain rule with trig functions and stuff. But most of the derivatives you see, they're just going to be polynomials like this, and you can just follow this rule for polynomials. But the derivative, if I imagine that I have a 1 right there, the derivative is going to be 3 times 1 times t to the 1 minus 1. That's t to the 0, right, which is just 1, plus 2 times 2 times t to the 2 minus 1, which is just t to the 1. And then for this 4, I assume that it has a t to the 0, right? Because t to the 0 is 1. And then I can apply this rule for polynomials. So it's going to be minus 4 times 0 times t to the 0 minus 1. But because you have that 0 that you're multiplying by, this whole thing just goes away. Basically, the derivative evaluates how does something change with respect to some other variable. And since this is a constant, it doesn't change. And so the derivative of a constant is always going to be 0 because it's unchanging. And the derivative measures how something changes with respect to another variable. It's actually pretty groundbreaking for Newton to come up with this was a big deal. So and then so if I just evaluate this, 3 times 1 times t to the 0 is just 3, plus 4 times t to the 2 minus 1, which is just t. And then I can evaluate it at t equals 3 seconds. That's going to be 3 plus 4 times 3 seconds. As Courtney said, that's 15 meters per second. All right, now I also want to know what is the acceleration at t equals 3 seconds. What you're going to be doing is taking the derivative of this function, which is the velocity function. You'll look at it pretty quickly and tell me what is the acceleration at t equals 3 seconds. What is it? 4, right. So the derivative of this, if I write it as 3t to the 0, 4t to the 1, it's going to be 3 times 0 times t to the 0 minus 1 plus 4 times 1 times t to the 1 minus 1. But as you've all said, it's just equal to 4. So my acceleration at t equals 3 seconds, in fact, my acceleration at all times is 4 meters per second squared for the life of this function. And then the velocity at t equals 3 seconds is equal to this. Now the velocity is going to change. So for example, at t equals 5 seconds, this is going to be 3 plus 20 or 23. So the velocity will increase. In fact, what type of function is this? What's it going to look like? Right. Do you have a special word for it? It's a parabola, right? So it's a quadratic function which produces a parabola. All right. All right, we'll come back to that and we'll work through some more problems. I know that some of you, either you're just in calculus and you haven't really done this thing, polynomial derivatives and all that jazz, but we'll come back and do another example problem next time. But right now, let's look at motion of plots. If you're in the lab, is everybody, some of you aren't in it, are you? Who's not in the lab? Okay, well, quite a few of you. We'll spend some time on this, but you also do it in the lab. If you're not getting it, come see me, I'll help you. But the lab will also help you with this. We're going to look at motion that's represented in plots, not quantitatively, but just qualitatively. And you just need to be able to describe the motion in those plots. We'll do a number of examples. But first of all, let's just start with this simple one, right? How would you describe the velocity of this plot? First, is the velocity of this object positive or negative? It's positive, and you know that because the slope is positive, right? This has a positive slope. Is the velocity increasing, decreasing, or staying the same? It's staying the same because the slope is constant, right? And I think that's all. So we have well, what is the acceleration of this plot? Okay, it's constant, but it's also 0. It's constantly 0. Because if the velocity stays the same, that means it has 0 acceleration. So here I have a positive velocity. I have a constant velocity. And then wrapped up in that constant velocity is also acceleration equal to 0. Or what about this next plot? Does it have positive, negative, or 0 velocity? it has positive velocity because the slope of this plot is always positive. All right. What about is the velocity increasing, decreasing, or staying the same? It's increasing. It's speeding up because you see the slope here is small, but then the slope gets bigger as it goes up. It gets steeper. So here I have a positive velocity, an increasing velocity, and an acceleration that's positive, negative, or zero. Positive, very good. So we think back to those rules. If the velocity and the acceleration are in the same direction, it's going to be speeding up. In this case, it's speeding up in the positive direction, so it has to have a positive acceleration. All right, how about this next one? Positive, negative, or zero velocity? All right, it's just sitting there. Right, it's sitting at x equal 1 meter, or whatever the position is, and as time goes on, it doesn't move. So it has zero velocity, also zero acceleration, as it may be. So the velocity equals zero. All right, how about this one? On the left, positive, negative, or zero velocity? That's this one right here. It's positive, right? So the slope here is always positive, so I have a positive velocity. Is it increasing or decreasing?
Increasing.
It's what? What's the velocity doing? I'm hearing both answers. Is it increasing or decreasing? So ask yourself, what is the slope doing? And then that'll tell you what the velocity is doing.
It's getting less steep.
It's getting less steep, so that means it's doing what? It's decreasing, right? So the slope is big initially, and then it gradually gets smaller. So that's a decreasing velocity. I understand what you're thinking, because the position is increasing, but we're not looking at what the function is doing, we're looking at what the slope of the function is doing. So here I have a decreasing velocity. And that means the acceleration is what? Positive or negative or zero? Negative, right. Go back to those rules. It has a velocity in the positive direction, but it's slowing down. That means it has a negative acceleration. The velocity and the acceleration have to be in opposite directions. So it has a negative acceleration. All right, one more. We'll have a few more next time when we come back. Let's do this last one. Here we have two segments, positive or negative velocity. What? Negative velocity right here. And how about right here? Positive velocity. Is the velocity at this point positive, negative, or zero? Positive. You sure? Yeah, it's positive right here. It doesn't matter that it crosses the origin, that it's at x equals 0. All that matters is the slope. So on the left-hand side, I have a negative velocity. On the right-hand side, I have a positive velocity. And in all cases, because the slope isn't changing, I have acceleration equal to 0. Except at this particular point right here, and something funny happens there. All right? All right, folks, I think that's all of our time. Again, I'm not going to be around, though if you have email, I'll certainly get email. On Thursday, guys, for the Chem majors, there is like a potluck kind of thing. I think that we'll be out in the quad, and then we'll also be up in the physics lab, I think, depending on the weather, I guess. And that's going to be at 4:30. So y'all come, we'll be food, hamburgers and stuff like that. And you can sort of hang out, students will be there. Back. All right, have a good day.